In this video, we'll look at the Gram-Schmidt process. The problem is to find an orthogonal basis for the given span. First thing we'll do is grab our first vector, let's call it v1. And that vector just gets added to our set. So this set x here, that's what I'm going to call the partial basis. And this set will be updated after each step. After each step, we'll be adding a new vector to this partial basis. For step 2, our second vector consists of the second vector in the span, the 2, 1, 1, 1, minus the projection onto x of that vector 2, 1, 1, 1. So we've got 2, 1, 1, 1. And we're going to be subtracting off the projection of this vector here onto this vector here. So we'll be doing the dot product of these two vectors, which gives us 3. And everything else that we're going to write down is about this basis vector here. So we're going to be dividing by the dot product of this vector with itself, which is 4, and that's in the direction of this basis vector 1, minus 1, 1, 1. Now what we really care about here is the direction of v2, so we are free at any point in this process to clear the fractions. We can multiply v2 by any multiple that we like, so why don't we go through and multiply it by 4. We'll multiply that first vector through by 4, and that gives us 8, 4, 4, 4. Multiplying the second vector through by 4 is just going to clear that fraction, so we'll say minus 3 times 1 minus 1, 1, 1. And that gives us 5, 7, 1, 1. So now that we're done this step, we're going to update our partial basis. X now consists of that first basis vector as well as this vector 5, 7, 1, 1 that we just found. Now it's important to check after each step that we've done everything correctly. So we're just looking at these two vectors here and checking that they are orthogonal. Yeah, they are. That convinces us that we have not likely made an arithmetic mistake at this point. Now on to the third step. v3 is going to be our third vector in the span. That's 3, 1, 1, 1, minus the projection onto x of that vector 3, 1, 1, 1. So at this point we're calculating v3, which is our third vector in the span, minus its projection onto x, and I've recopied the partial basis x from our previous step. So we're looking at 3, 1, 1, 1, minus, we're first going to project this guy onto our first basis vector. So taking the dot product of these two vectors here is going to give us 4. And everything else we're going to write down is going to be about this basis vector here. So dot product of this vector with itself is 4, and that's in the direction 1, minus 1, 1, 1. Now we still need to project our vector 3, 1, 1, 1 onto our second basis vector. We're going to be subtracting off that projection as well. So taking the dot product of these two vectors here, we've got 24, and everything else we're going to write down is going to be about this basis vector here. So dot product of this guy with itself is going to give us 76, and that's going to be in the direction 5, 7, 1, 1. So let's think about simplifying these fractions here. This 4 over 4, that's really just 1. This 24 over 76, let's call that 6 over 19. And just like before, we're free to clear these fractions here. We can multiply v3 by any non-zero multiple that we like, and that will not change the direction of v3. So let's take 19 v3, multiplying through by 19, And then our second vector, that's going to get multiplied through by 19 as well. Multiplying the third vector by 19, that's just going to clear that denominator there. So we're going to have minus 6 times 5, 7, 1, 1. All right, so let's work out what 19v3 looks like. We've got 57 minus 19 minus 30 gives us 8. 19 plus 19 minus 42 gives us negative 4. And then 19 minus 19 minus 6 gives us negative 6, and that fourth component comes out to negative 6 as well. All right, so our basis after this step then consists of the vectors 1, minus 1, 1, 1, 5, 7, 1, 1, as well as this new vector that we've just produced, 8, negative 4, negative 6, negative 6. Now, you may have chosen to scale this. You might have divided each of the components through by 2. So if you used 4, negative 2, negative 3, negative 3 instead, that would be fine here. What we're checking is that this set here is an orthogonal set. Each pair of vectors here do have dot product 0. That tells us all our vectors are orthogonal. And so we have succeeded in finding an orthogonal basis for the original span. So the idea here is that the span of the set X is equal to the original span that was in the problem. But any calculations that involve this span are now simplified because these vectors in X are orthogonal.